Hello, folks. Welcome to our session. Today, we will discuss how to ensure that your data is fresh and searchable using Nexla and Pinecone. I am Amay Desai. I lead AI at Nexla. We have Corey with us, who's a staff partner engineer at Pinecone. And today, we are going to talk about embeddings, which Corey is going to go a deep dive into. As you know, embeddings are a fundamental component to improve searchability in GenAI as well as RAG products. After that, I will introduce us to Nexla, and then we'll talk a bit more about how Nexla and Pinecone can accelerate your enterprise RAG journey. And at the end, we'll have question and answers. All yours, Corey.
Thanks, Amy. So as Amy said, today we're going to talk about a couple of different topics. Notably, we'll explore RAG, or retrieval augmented generation. But before talking about that specifically, we have to ask ourselves, how does RAG work behind the scenes? The answer to that question is embeddings. So what are embeddings? Simply put, embeddings are numerical representations that capture the essential features and relationships of discrete objects like words or documents in a continuous vector space. So here we can see we have data, and it can be of any kind really, but typically text for the purposes of our discussion today. We can see the data being passed into an embedding model, which extracts features of the text and returns a list of numbers that represent those features. There are many different embedding models you can use, ranging from open source to closed source. The important thing to understand is that embedding models convert our input data, such as these queries, into lists of numbers known as embeddings or vectors that can be upserved and stored in a vector database. Importantly, these vectors capture the underlying meaning of the text or other data that was applied to the model. Embeddings are dynamic, they're context sensitive. They capture the essence of the data they represent, but are influenced by the context in which they are used. For example, embeddings trained on general text might not perform as well in specialized domains like medical or legal text. While this adaptability makes them powerful, it also requires careful consideration when choosing or training models for specific applications. You'll forgive me for the pun, but here's an example you can bank on. You can see that we have three examples here. Where is the Bank of England? Where is the grassy bank? And how does a plane bank? I've highlighted the word bank in blue 3 times. And you'll notice that even though the three queries contain the same keyword, bank, the vectors that represent their meanings, shown here as blue dots and arrows, are spaced further apart. This is because the queries are talking about different things. So bank in the Bank of England is pretty far apart from how does a plane bank. And you can see they're sort of shooting off in different directions and they're landing further apart. If you notice at the bottom of the slide, we have 2 phrases. The bees decided to have a mutiny against their queen, and flying stinging insects rebelled in opposition to the matriarch. There's not a lot of repetition between these sentences. You don't see a whole bunch of blue highlights like you did in the top 3, but you'll notice that the 2 phrases have resulting vectors that are very close together in vector space. The embedding model has extracted the semantic meaning, and that means that these vectors are next to each other because they're saying essentially the same thing, just with different words. That's a really powerful, exciting, and useful feature of vectors. So to better understand embeddings, let's visualize them in a 3D space. Here, each point represents a word, and the distance between points indicates their semantic similarity. So once we have vectors, we can upsert them to a vector database such as Pinecones, which means send them into the database. Vector databases work by grouping similar vectors closer together and dissimilar vectors further apart. Here we see the embeddings in high-dimensional vector space. This means that vectors which are similar, such as the names of days of the week, they'll be grouped closely together. Vectors whose features are dissimilar will be spaced out further apart. So vector databases very efficiently model relationships between anything you can vectorize. So those were pretty high level and relatively dense the concepts. I'm going to go into some more concrete examples now, and then I'll encourage you after we unpack some ideas to repack them for yourself with a thought exercise. From there, we'll tie this back to the first few slides, and then we'll go on to the Amy's part of the presentation covering RAG. So Timothy Baldwin at the University of Melbourne in Australia and a few pals explored one of the curious mathematical properties of vector space, that adding and subtracting vectors produces another vector in the same space. What do you get if you start with the word king and remove the word man from its definition, then add in the word woman? That would be queen. Semantically, a queen is simply a king if you replace a man with a woman. The same thing happens in vector space, where deleting the embedding values for man from those of king and replacing them with the values for woman gives you a vector representation of the word queen. Another example of vector math and substitution. If you take the vector representation of the capital city Paris and remove the values for France while adding those for Poland, the resulting vector representation would be equal to Warsaw, as the semantic relationship of Paris to France is equal to that of Warsaw to Poland. So how does this magic math work? Well, put simply, vector databases work by grouping similar vectors closer together, dissimilar vectors further apart. If you remember kids' puzzles that are connect the line, you see that a lot of these are straightforward, while others provide hesitation. So let's look at these three columns. First column lists coffee, hospital, music, restaurant, and school. The second and third columns contain words that could be associated with these. Well, let's think about how these words would represent in the visualization. Ask yourself, how would these words on the right show up? Imagine the clusters. Which words are hard to envision and which ones are easier? So let's try looking at caffeine. So how does this magic math work? Well, remember the vector databases work by grouping similar vectors together and dissimilar vectors further apart. If we think about kids' puzzles that connect the line, we see that a lot of these are straightforward while others provide hesitation. So let's look at these three columns. First column lists coffee, hospital, music, restaurant, and school. The second and third column contains words that could be associated with these. And let's think about how these words would represent in a visualization. Ask yourself, how would the words on the right show up? Think about what the clusters might look like and which words will be clustered together and which ones will be further apart. And pick out a few words and think about where they would be. Try caffeine or cup or exam. Actually, let's specifically consider exam. This word could relate to a hospital visit or being in school. In vector space, exam could be close to words like doctor and patient in the context of a medical exam, or near teacher and student for a school exam. This multidimensionality allows embeddings to capture different meanings and contexts of the same word. We're going to shift gears a little bit, and we're going to look at the color wheel. If you're colorblind, red is on top and green is on the bottom, and the colors are labeled on the outside of the wheel. So let's say that you live in green and you decide to drive clockwise away from yellow. If you go 2 stops, you'll wind up in blue. Conversely, if you decide to drive away from red and get off after 2 stops, you'd end up in orange. So using this logic, you end up with the understanding that green is to blue as, next slide, red is to orange. But is that really accurate? Relationally, they're similar, but what would that mean for the embeddings? So the analogy green is to blue as red is to orange attempts to illustrate relationships between colors, but it falls short in capturing the complexity of word embeddings for several reasons. First is the simplicity of the relationships. The relationship between colors is relatively straightforward and linear. Colors can be easily mapped on the color wheel, and the relationships are based on simple attributes like hue, saturation, and brightness. Word embeddings, on the other hand, capture much more complex and nuanced relationships. They consider context, usage, and semantic meaning, which are not as easily represented by simple linear relationships. There's a lack of context. The color analogy does not account for the context in which the words are used. For example, from earlier, the word bank can mean a financial institution or the side of a river, depending on the context. Embeddings capture these contextual nuances, which the color analogy cannot. Colors do not change their meaning based on context, making the analogy less effective in illustrating how embeddings work. And dimensionality. Colors are represented in 3 or 4 dimensions, whether it's RGB or CMYK, whereas word embeddings exist in high dimensional spaces, often hundreds or even thousands of dimensions. And this high dimensionality allows embeddings to capture intricate relationships and subtle differences between words. The color analogy oversimplifies this aspect, failing to convey the richness of the information captured by the embeddings. So, what is the TLDR? The most important thing to understand is that embeddings are numerical representations of data. They capture both semantic meaning and allow for efficient comparison of similarity. So vectors whose features are dissimilar will be further apart in the vector database. This allows vector databases to efficiently model the relationships between anything that you can vectorize. So the key points to take away from this is that embeddings can represent various data types, not just text. The choice of embedding model will affect performance in different tasks. Dimensionality balances the information capture and computational costs. Context sensitivity affects interpretation and application. Embeddings have a number of applications for their use: RAG, semantic search, audio search, anomaly detection. But now we're going to shift focus slightly and focus on one in particular: retrieval augmented generation, or RAG. I'm going to turn things over to my colleague Ame, and he's going to explain how Nexla and Pinecone together empower RAG. Ame?
Thank you, Corey. I'm back to introduce you about Nexla and how Nexla and Pinecone can be worked together to accelerate your GenAI products, specifically RAG. So about Nexla. Nexla is a data plus AI integration platform. It's designed to simplify the complexities of working with data. Our mission is to provide ready-to-use data for GenAI analytics and operational applications. Nexla's platform today is trusted by numerous customers where they use Nexla to parse, ingest, validate, transform, and deliver data to wherever they need in a scalable and seamless manner. We proudly also serve a diverse clientele across many verticals over the last few years. So, enterprises today, both small and large, face the challenge of managing data across diverse systems and formats. From data warehouses to homegrown system, SaaS services like SharePoint, Salesforce, as well as diverse data formats like PDFs, Parquet files, EDI, the landscape is pretty complex. While many solutions address specific data integration challenges and use cases, Nexla is a converged integration platform that can meet all of your downstream needs, whether it's an analytical system, generative AI, unstructured data, whichever is necessary. With Nexla, you can achieve seamless data integration and management, ensuring your data is always ready for use. So, how does all of this is made possible? It's made possible because of NextSet, which is a unique proprietary data product architecture that we have developed over the years. Next sets enable anyone to understand and work with any data set in a familiar and consistent interface, graphically as well as via an API. And that is a small representation here that we are presenting on the slides. No matter where the data comes from or what format it is in, you'll always see this familiar NextSet UI, and you'll be able to transform and deliver your data where you need. As soon as you connect your data in our platform, you're working with next sets, which in addition to your raw data also allows you all of these other goodies, samples, schemas, things around data characteristics, things around data monitoring, as well as error management, which play a critical role in our mission of ready to use data. And we'll also talk about how next sets help with RAG just in a bit. Next, we're going to talk about retrieval augmented generation for enterprises. And RAG has kind of been on a tear over the last 2 years since the invention of LLMs. So for RAG, there are typically two steps. The very first step is just ingesting data and converting your data or documents into vectors. So you would read data from a variety of, again, different sources, chunk them, generate embeddings, and you could use many embedding models. We are presenting just one example here of OpenAI, and then push those embeddings into a vector database like Pinecone so that you can leverage that later for downstream use cases. The second step is a real-time workflow where you use an LLM in accordance with a vector database like Pinecone. So typically here, a user would send a question to a chatbot service, which could be either as a UI product or simply an API, where the question first comes, an embedding for it is generated. The embedding is sent to a vector database like Pinecone, which searches for relevant vectors very quickly and then sends you back context that's relevant to the question that the user asked. This context then is kind of prepared, or for a lack of a better word, is stuffed to an LLM, which then synthesizes a response to the question as well as to the context that was given to it. This is the typical vanilla RAG flow that anyone, everyone today can get started on very quickly. Next, we'll kind of talk about challenges with both of these steps. So, number one, as we just mentioned, one of the big challenges is just integrating all the diverse data across enterprises today in a vector database Pinecone. Nexla has built 500 plus connectors over years for different systems as well as different formats. And one of our core strengths is our ability to deliver a connector in minutes rather than weeks, days, or months. This allows you to build pipelines in 1 year converged integrated platform, as I mentioned before. Next, once data is passed, you need to chunk your data before it can be embedded in a vector database like Pinecone. Here, you need to figure out a strategy that can balance performance, cost, quality, as well as constraints of embedding models like context window. Nexla allows users to do this in an experimental manner in either no code or low code to quickly figure out the best strategy for their use case. Another challenge is data is just dynamic. There are frequent updates that happens to documents like HR policies, rental leases, which kind of change every year. Nexla ensures that because of its next set concept and a very deep understanding of metadata, that you can only process the latest changes. This ensures data quality not just in Pinecone, but also controls cost across the board for you. Next challenge is actually at the generation level of the RAG use case. So today, users, when they send a query, one of the key aspects that is missing is providing additional context from private enterprise data or private knowledge bases to the prompt that's eventually going to be sent to an LLM. And this is again a problem of data integration because you need to integrate across various different knowledge bases. But you also need seamless orchestration to be able to work across these diverse data sets. Furthermore, certain data, tabular data specifically, that is stored in data warehouses, or very, very structured data that's coming from various APIs from the web or potentially internal enterprise systems, may not always be suitable to be stored as embeddings in a vector database like Pinecone. This adds another layer of complexity to the orchestration problem that we have when trying to solve RAG. Next, we are kind of going to look at a demo of the Nexla product and how you can do both of these steps of ingesting data into Pinecone, as well as asking questions of your data once it is present in Pinecone. Let me tell you a bit more about how we set up a SharePoint source within Nexla. So I'm going to just pause this flow so that we can take a look at it in the edit mode. All right, let's take a look at the legal filings SharePoint source now. So here is how the SharePoint source is set up. This is kind of where the data is coming from. We are strictly looking at PDF files. We have also set up a scheduling, which is to process it at 7 o'clock daily. We want to read this as a PDF file in the text parsing mode. And we're not going to generate embeddings for now, but these are roughly the options that we have today. And we also are using like the Nexla SharePoint credentials, as well as a variety of other things that you can see around here, around metrics for the data that was processed and how it was processed. Let me go into the edit mode now. So all of that information that we just presented kind of was coming from here. Here we can see that we can read it as a PDF file. There are actually 4 parsing modes that we support out of the box. One is just standard text parsing, which is done using Nexla's native parser. But we also have deep integration with AWS TextRack so that we can leverage machine learning models and OCR from AWS TextRack to be able to parse PDF files correctly, as well as Tesseract, which is an open source package for OCR for just parsing PDF files, especially with images. In addition to this, we also support unstructured.io, where you can read data as unstructured files, and you can select chunking strategy kind of right out of the box here as either by title or with a default strategy. I'll keep this as is since we have kind of already set this up. But if you scroll down at the very end, you can see kind of the scheduling and how that is done. There are a variety of options here for different time resolutions for when the data can be processed. And this is how we are also able to check. Right now, this particular scheduling setup is for every day. So every day, if there is a new file available, we'll only process the new file, but not the other files. And that ensures that your embeddings are fresh, as well as we don't like recompute the embeddings that you've already generated. So let me go back to the rest of the data pipeline now. So once And I'll just activate it also. There's no reason to keep paused. All right. So once the pipeline is activated, this is the source next set, the very first next set that is created. Once the source next set is created, we did a very simple metadata transform. And this was very straightforward Python code where we just extracted the file path and the page number because we want to leverage Pinecone's metadata feature to store this information as it is useful for citations down the line. Post that, we did semantic chunking, and we are doing semantic chunking using a GPT-4o mini model so that we can only create chunks whose concepts are same or similarish, and we rely on an LLM to be able to do this. One key aspect that I want to point out though is you can leverage any LLM here, not just GPT-4 or the GPT models, but it allows you to scale up your data as you're parsing to any LLM service that is out there. And Nexla has solved this problem not just for this small set of records, but at larger scale too. Post that, we actually leverage an embedding model that Pinecone serves today, which is an open source model called as multilingual that's served by Microsoft. And the context window for Pinecone is about the Pinecone embedding model is 512 tokens, which we take care of in the semantic chunking itself. And once that data for embedding is generated, we just send it to a destination, which is Pinecone with the upset vectors API that Pinecone has exposed. Additionally, I also want to showcase that we can also generate OpenAI embeddings. So this is the exact same data flow. The data generated after semantic chunking is roughly the same, but instead of using the Pinecone embedding, we can showcase OpenAI embedding and then send the same data to upset vectors via Pinecone. Notice how there are errors at different stages of the pipeline or a different life cycle of the data flow. None of this impacts the data pipeline as it is set up. The records that are correct will be processed and will be ingested into Pinecone. And then you can go and see what the errors are post the ingestion is done without any interruption of your pipeline. That is typically present in our notifications tab. And here you can see that it just says that the vector dimension 0 does not match, which effectively means that the embedding that was generated was empty. And that is largely because the text that was passed was either too little or was not passed correctly by whichever method we chose. But it allows you to still build data pipelines with resilience and robustness and not get hung up on a variety of different issues. One other class of issues that could happen, especially when using LLMs, is LLM services may not be available. And these are the 8 errors that kind of come across there. And even those are handled gracefully by Nexla so that your pipelines can stay resilient and robust. Here, this is an end-to-end example of how you can move your enterprise data in a source like SharePoint to Pinecone in a fairly quick and seamless manner. I'll close this for the time being and go back to a project that we have here in Nexla and showcase 2 more examples, though not in deep. One example here is from HubSpot, and this is getting the contacts data from HubSpot. Typically for sales and marketing domains, a lot of data has notes for opportunities, accounts, contacts, and we are able to take this data from HubSpot and again move it into Pinecone in again a very straightforward, seamless manner. Another example is of SEC PDFs that we just downloaded from the internet. These are all the SEC forms that are available, which anyone can get. We put those SEC forms on S3, and we're again able to do similar steps to get the data into Pinecone. This is the power of Nexla, where you can leverage multiple different connectors on multiple different formats and get data into Pinecone so that you can talk to your data, do, as Corey mentioned, a variety of other applications for RAG. The next aspect of RAG is the generation aspect, and we kind of want to talk a little bit more about that right now. We just briefly mentioned how we handle the lower part of this diagram, which is file management and ingestion, parsing, chunking, embedding, and kind of loading it into VectorDB. But then when you want to retrieve documents and get useful answers out of it, how can Nexla help today? We help that by building and orchestrating this advanced RAG framework that we have built, where first, when the user kind of question comes, we use a variety of different LLM models to rewrite queries, to classify queries, and to reroute queries accordingly based on the intent that we have learned. We are able to then retrieve data from Pinecone, re-rank it, filter it, use Pinecone's metadata filtering to get the right information if necessary, again in an automated agentic manner. And then additionally, we can add additional context from other data sets that you might have in your enterprise data systems, whether that is just straight up metadata, whether these are external APIs, real time data that you might have, or customer data that is present in other knowledge bases. And then finally, construct this context enriched prompt, do model orchestration in the sense of which model you would like to leverage to answer this particular context enriched prompt, and then send it to an LLM to finally get an answer. Even once the answers are generated, we have an evaluation LLM that grades the answers and decides next step of a strategy for how to extract the right answer for the user question. Let me jump onto another demo to kind of show you Nexla's chatbot. So here, this is Nexla's chatbot, which is genai.nexla.com. You need a service key to be able to access this public website. And the service key ensures that you, as a user, can only access data that you own, even if there are multiple concurrent users accessing data. The data sets that you access are strictly isolated only to you and no one else. I have selected here a SEC filings dataset that I just presented to you a while back of how we ingested that. And we have integrated with a bunch of LLM providers today that are listed here on the web page, and you can select a variety of different models that are present under them. So here, I'm going to ask a let's say a very simple question, things like what forms are related to bankruptcy. And I'm going to send this question to both Anthropic as well as OpenAI for generation part. But before all of that happens, we are actually going to retrieve data from Pinecone, re-rank, filter it as necessary, and prepare the exact same context and send to the two models. So both models in this scenario have the exact same context and are working on same set of documents. And this is how kind of the Nextla's chatbot starts generating answers. I'm not really going to get into which answer is better versus what. It's just a whole cut. This was just to demonstrate how you can use this chatbot to talk to your data in Pinecone very, very quickly. An interesting question that might be that I at least thought about asking was what fields are mandatory in Form 10K? And again, same question follows kind of the same sequence of steps. We get the answers back from different models at different streaming speeds, but hopefully this gives you an experience about how easy is it to search your data in Pinecone using the Nextla's chatbot. And we also do citations, so there is source information that's kind of present here so that you know exactly where the information is coming from. And each LLM may choose to present the source information in a different way. We are not yet trying to prompt engineer to optimize for an LLM. We are trying to keep the context exactly the same. Moving back onto our slides, hopefully this demo gives you a picture about how we are building and orchestrating advanced RAG today with Nexla. And hopefully it is useful for you. All right, so with Nexla, I think we can scale GenAI from prototype to industrial scale. One big reason for that is we have already ingested terabyte scale, both unstructured and structured data across all formats and systems. We have resilient pipelines with monitoring and notifications, as we have shown you. To really get this to work at industrial scale, you also need a vector database that can also work at industrial scale, that can process terabyte scale data. Pinecone is one of leading vector databases that can do that today. We have various customers who are using Pinecone today, processing thousands and millions of documents that are present. Nexla supports Pinecone as source for searching as well as destination for storing data. And we also allow you to use multiple algorithms for embedding generation. In addition to that, you can also enrich context from a variety of different data sets, which allows you to do rapid RAG with no and low code workflow and go from query to response very quickly. So hopefully this gives you a good experience of how you can use Nexla to scale your GenAI from prototype to industrial scale using Nexla as well as Pinecone. So if you love this, how can you start? With Nexla, we have a full featured free trial that you can sign up on this particular link, nexla.com/free trial. Additionally, Pinecone has a very good self-service product as well as a very generous free trial program. Highly recommend to encourage their serverless scenarios. And if you have both of those, you can then use Nexla to build data pipelines for your RAG use cases or any other use cases that you might have in generative AI. Push that data into Pinecone and then use genai.nexla.com to chat with your data in Pinecone. That's all we had for you today. Hope you liked it. If you have any questions, we'd love to answer those. So let's get into question and answers. We see a few questions for us. So I think actually the first question is for Corey related to Pinecone. So let me repeat the question. The question is, what are some of the core use cases for Pinecone today, and where are customers finding value in it?
That's a great question. So Pinecone's core use cases today include AI assistance, AI search, and classification and model training. The Pinecone Assistant, for example, leverages Pinecone's capabilities to deliver personalized and contextually relevant interactions. And AI search utilizes Pinecone's vector database to enable advanced search capabilities, providing more accurate, relevant results compared to traditional keyword based searches. Additionally, Pinecone is heavily utilized in data classification, curation, and model training, particularly for complex data types such as audio, objects, and video.
Perfect. That's Thanks for the information, Corey. Hopefully that answered the question. Uh,
Yeah.
the next question is actually for Nexla folks, and there's a question here asking how easy is it to connect to SharePoint. So I'm going to present actually that live so that we can quickly see how easy it is. So to see how easy is it to connect to SharePoint, we'll actually have to just click on new data flow. There are a variety of options of what kinds of data pipelines you can create. I'll just create the flex flow, which is the generic pipeline that we have. Here, these are like all the connectors that we have today, the various categories listed. Just quickly search for SharePoint. And here there's a credential that you can add. We already have the Nextcloud SharePoint credential, which we used. But if you want to add a new credential, this is the page that will kind of open up. All it needs is a tenant ID from Microsoft that you can find on your Azure page. And the authorize button will directly take you to Microsoft to do OAuth authorization. And that should be it for you to connect to SharePoint using Nexla. All right, I think that's all we had today in terms of time. There are some other questions that we have gotten. We'll definitely follow up answers to those questions either from me or from Corey, wherever relevant. But just want to thank everyone who tuned in and listened to us talk about embedding data and RAG. And if you have any other thoughts, please let us know as feedback either from me or Corey. Thank you, everyone. And thank you, Corey, for telling us about embedding
Yeah. Thank you,
Pinecone.
Nick. Appreciate it.